Okay, welcome back from this very short break. As promised, the second part of this tutorial will hopefully be a little bit more interesting because now we're getting into the question, how can I actually build certificates for my planner? And before we do that, however, I first need to tell you a little bit about how the certificate is actually structured in terms of what file we need to give to the verifier, how they are built up. So there is a not at all new GitHub repository where our verifier actually lives since today. The reason for that is that I'm in the middle of a rework and ideally wanted to finish that before the tutorial, but didn't manage. So this is now somewhat work in progress, but it is a fully functional version of the verifier. And yeah, it's nothing fancy. As you see also, it is definitely a lot smaller than any planning system. It has a little bit of an explanation how to install it. It also talks about the file formats that you need to feed it with some very nice ASCII art. So there you can get the verifier and try out your certificates. And what you need to actually create the certificate is you need two files mostly. First of all, you need a description of the task. Currently, that is limited to just strips tasks, and you also can't just feed it the PDDL. It needs to be a grounded version. We defined our own file format for the moment. Ideally, in long term, you would just feed it the PDDL. And one other thing is strips with negation is coming soon. We actually had an experimental branch where we implemented that. But yeah, coming soon, TM, who knows how soon, whenever we get to it. But it theoretically exists and it works. And in this task description, we described the variables, actions, goal, and initial state. An important thing to note there is that in the certificate file, we actually refer to the variable and actions as IDs. So we have first a list of all variables where they actually have names, but then in the certificate, we refer to them just by IDs, and that is just based on occurrence. I will show you an example in a little bit. The second, more important file in a way is the certificate file. And there each line is one of three things. So either it is a state set expression, that's where the E comes from. These lines always start with E. And you need to give each state set a unique ID. Then you need to say which type it is. So is it a Horn formula? Is it a union? Whatever. This is all encoded in this third letter here. As I said, description is on the GitHub repository. And then there's the actual description of the state set. That depends, of course, on which type it is. The second thing you can define is an action set. That line that defines action set starts with A, again has an ID, says which type it is, and there are actually only two. There is the type A for all actions, so the actions of the planning task, and then there is the explicit enumeration. And the third type of line that you can have is a statement line or knowledge line, so that's where the K comes from. That is what we have seen before in these high-level certificates, these pieces of knowledge that we collect, these statements. These you specify with, I see also there is an unsorry for that. So you start the line with K, you give it an ID again, you say which type of statement it is. It can be a statement about deadness, statement about subsets, or statement about unsolvability. Depending on which type it is, you need to say which set IDs are you talking about. So this statement says that state set 7 is dead, and then you need to give it a justification. So here, this is subsetted, the inference rule, and the premises for the inference rule. And optionally, BDDs are described in additional files simply because it was a bit easier to work with the CUD library that we use for representing BDDs. So these need to go in a separate file. You may or may not have these. As I mentioned before, there is a detailed explanation in the README file of the GitHub repository. But let's look at a small example. So as I mentioned before, what we have seen so far was these high-level proofs with like these numbers, statement, justification. The corresponding certificate file has a little bit more lines, and that is mostly because we need to define these sets and state sets and action sets. So here, the first 3 lines actually just define some state sets. The first line defines a constant empty set, so that's the CE. So that is just this symbol here. Then state set number 1 is the constant set containing the initial state, that's the I here. And then we define an action set with the ID 0, and that is the set of all actions. And now we actually get finally to our first piece of knowledge. So that corresponds to this line here. We say the set number 0, which is the empty set, is dead. And we show this with using the rule ED. And so on and so forth. I won't go into detail with everything here because I have an additional low-level certificate that I want to show later. But what I do want is to just show you how you run this then. So we have here this file cert1, it's called. That is it. Oh, maybe first. So that is exactly what I showed you. These are the exact same lines. And in order to run this, we need to just run our verifier. I compiled this already in a subdirectory called Helmert. And the verifier needs 2 files, a task file and the certificate file. And the good news is in this run here, it doesn't complain about anything. It doesn't say this statement is not correct, because it will loudly complain if something's not correct. What you do see, however, unsolvability has not been proven because we never showed unsolvability. Like there was no statement showing unsolvability. So it will tell you at the end, even if all your rules, applications and everything are correct, if you in the end didn't show unsolvability, it will complain about that. Okay. Then let's get to building our very first certificate. And for that, we look how blind search can build a certificate in this proof system. If you recall the completeness proof from before, we actually have seen already how a high-level certificate for this can look like, because in this completeness proof, we argued with the set of all reachable states, and that is exactly what a forward blind search actually expands. So we have this set. And just as a small side note, you can also do this for backward search. You need to change the certificate a little bit. So instead of showing that we don't have any alive goal states in the set, we show that the initial state is not in the set, and we show that the regression is kind of backwards inductive. So the reachable states are backwards inductive. And then we finish by showing that the set of all goal states is dead because it's a subset of the backwards reachable state. So very similar, just small changes to the proof. Okay, and here I want to show you now really piece by piece how we can create this low-level certificate that the verifier can actually read from this high-level idea. Again, we start with defining just some sets. As I said before, this constant empty set, that is our set number 0. That's very often the case. Set number 1 is the set containing only the initial state. So I always write it here on the side to have a bit better idea what this actually means, this line. Set number 2 is the constant set of all goal states. And action set number 0 contains just all actions of the planning task. And as before, our first piece of knowledge is that set number 0 is dead. So the empty set is dead. And we conclude that by using the rule empty set dead. Now, for the next statement, sadly, we need to introduce, again, a couple of set expressions. So set number 3 is going to be our set of all reachable states. This, of course, depends on the task, what this actually is. So I just wrote dots here. Then we need to define set number 4 is the progression of set number 3, so the reachable state, with the action set 0, that is what the 0 here means. So the progression of a state set with an action set. So that gives us this expression here. Set expression number 5 is the union of set number 3 and set number 0. So the reachable state union the empty set. And then our first piece of knowledge is exactly what we say here. We know that something is a subset of something. So set number 4, which was this progression that we defined, is a subset of set number 5. And we show this with the statement B2. Next, the next statement was that the intersection with all goal states is a subset of the empty set. So we need to define this intersection again first. That just says set number 6 is the intersection between set number 3 and set number 2. And then we can say, okay, set number 6, which is this intersection that we just defined, is a subset of set number 0, our empty set, with showing this with statement B1. And by the way, just a small word of caution, if you were to turn here 2 and 3 around, then you would say SG intersect R pi, which we all know is the same thing, but the verifier actually does not know that. So if you were to turn this around and then want to later on use a knowledge that something like this is dead, the verifier will actually complain and say, this doesn't work out. So the verifier really just works on a syntactical level with all this. You need to pay attention in which order you do things. Okay. Next step is thankfully straightforward. We don't need to define any more sets. We want to say that state set number 6 is dead. Number 6 was what we defined here, the intersection with the reachable states and the goal states. And we know this with the inference rule subset dead with 2 and 0. So that now refers to knowledge. This is actually the first time where we need to have some premises. So subset dead requires 2 premises. The first one is that a certain set is dead. And the second one is, oh, sorry, here, this was the subset statement. Here we say this is a subset of the empty set. And then knowledge number 0 was that the empty set is dead. So this is basically, I have the numbers wrong here, but this is basically the exact same thing. We just tell the premises here. Then the next statement was that the set of reachable states is dead. This we concluded with this a bit more complicated rule, progression goal. Again, you see here we just mapped the ID knowledge IDs one-to-one from the high-level proof to the low-level proof, and with that we can conclude that set number 3, which is our reachable states, is dead. And you've all seen it a couple of times already now. The next step is the set containing the initial state is a subset of the reachable states. This is shown with just statement B1. Again, just match the set IDs. From this, we can conclude again with subset dead statement that the initial set containing only the initial state is dead. And now we can finish our proof with knowledge number 7. We can say that the task is unsolvable, and we use the rule conclusion initial. And for that, we need to know that the initial state is dead, and that is exactly our knowledge number 6. To also give a small showcase how that works, we have here this cert2, which is what I just detailed here, all these steps. We have actually a very simple task that I used before already, but only now it's kind of important. So the task has only 3 variables. At first, variable A is true. We want that C is true. And we have 3 actions. The first one says we need A to be true. This makes B true, but deletes A. The second one is exactly the reverse with B. We need B to be true, makes A true, but quite trivially an unsolvable task. And the set of reachable states is actually here, it's described as an explicit enumeration. It uses a hex format that maybe takes a bit of time to get used to, but I can just tell you this is the state where only A is true, and this is the state where only B is true. These two are our only reachable states. And if I try to verify this now, it will tell me, yes, unsolvability has been proven, this certificate is valid. So our first actually functioning certificate. I have some remarks about implementation details. So depending on which blind search algorithm you run, there can details that will actually affect performance. For that, it mostly depends what search your best advice to just go with BDDs, because that's usually what symbolic search anyway uses. So there you can just take your BDD, your closed list BDD, and that is actually a certificate already with this little bit text around it. You need to be careful, however, if you were to use a symbolic search algorithm where you don't have a single closed BDD. I don't know if that's really common, but there are these like donut versus pizza models. You would need to build the union of all these closed list BDDs, and that can actually become quite costly because BDDs can do bounded conjunction and disjunction, but if you have many layers, this can actually become quite costly. But if you have a singular closed BDD, this is very cheap to build because you really just need to write that BDD out and this little bit of text. On the other hand, if you use explicit search, you could use just an explicit enumeration, or you can also use BDDs. For BDDs, you can basically add one state at a time to the BDD. There you don't really have this problem of unbounded conjunction because you always add a full model. So that can actually also be done efficiently. And you can do both, whichever you prefer. It depends a bit if you want your certificate to be generated fast or if you want it to be verified fast. Because if you want fast generation, you just write out the states. You have them in your closed list, you just write them out. But verifying explicit enumeration tends to be a bit slower. With BDDs, you just have this one BDD that you need to apply all actions to. And that is a lot faster to verify usually, but you add more overhead to the planner because you need to extra build this BDD. The second question is, when do you actually want to build the certificate? Again, there are two obvious choices. You can build it during searching. So every time you see a new state, you just write it into your certificate. However, that's a bit unnecessary if your planner is not only tailored for unsolvability, because you might have solvable tasks and then you write all your expanded states in a certificate that in the end you need to destroy because there's no certificate to be written. So what I usually prefer is to rather try to move it to the end. This gives you a bit more overhead because you need to iterate over the entire closed list again, but it's also a much more localized code change. You can measure the time it takes better, the overhead it creates. So overall, I prefer the idea to move everything that you can at the end. Okay, the next search strategy that I want to take a look at is heuristic search, which is probably one of the most popular search techniques. So the problem we have with heuristic search is what I mentioned in the first part. We don't really explore all reachable states anymore because we have these dead ends where the heuristic tells us, don't bother looking there, this will not lead to a goal. But this means the heuristic must have somehow been able to figure that out. So it must have some form of argument that this dead end is actually dead. So what you can do then is collect all these arguments for all these states, and then you can argue the following way. You know that the set of expanded states contains no goal state, else you would have a plan. Next, you know that the set of expanded states can only reach itself and dead ends, because these are the only ones you didn't expand. From this, you can conclude that the set of expanded states is dead, again with this rule progression goal. So you can only reach yourself or dead states. You don't have a goal anywhere there. So the set of expanded states is dead. And then the end, as usual, the initial state is in this set of expanded states, and thus it must be dead, and the task must be unsolvable. So here I'm just going to describe a high-level certificate now, because it gets a bit too big. I will show you a small example afterwards how such a certificate might look like on an actual planning task. But on the high level, we first now just assume, okay, we somehow have this knowledge already that each dead end is dead. So all these here are dead ends, and we know already that they are dead. What we can then do is conclude more and more that the union of all dead ends is dead. And I add an extra step here. I'm actually not going to work with the union of these dead ends, but rather with a new set called the set of all dead ends, SD. I do that because I will explain it later. It can be beneficial depending on which representations you have. So here, this is basically, this SD is exactly the same set. It's just a fresh description of this set. So this is one concrete set that captures all these dead ends. And since we know that the union of all this is dead and this set is equal or a subset, we know that this set SD must be dead. And then we can, as I explained before, we can say the progression of the expanded states with respect to all actions is a subset of the expanded states and the dead ends. We know there is no goal state in the set of expanded states. So just another way to express that. Thus, we know that the intersection between the expanded states and the goal states must be dead. From this, we can, as I said, with rule progression goal, we can conclude that the set of expanded states is dead, which means the initial state, which is a subset, or the set of the initial state is a subset of this, means that is also dead, and the task is unsolvable. Before looking into how we show the single dead ends dead, I mentioned before that I use this extra set SD, and this has the reason the statements that a certain dead end is dead, they might actually use different representations for these dead ends. So maybe for one dead end, we used two CNF formulas, and for another one, we used VDDs. And there we have this problem again that we can't just mix and match formalisms wildly. We have strict rules on that. So one thing you can do is, because we are only talking about single states, you can use statement B4 to build an explicit set containing only this dead end and show that this is a subset of the same dead end, just in different formalism. This will produce very low overhead because one state explicitly written down is very small. And then you have two options. Same as with blind search, you can either build your expanded states as explicit set or as BDDs. If you want to go the explicit route, you can actually do this quite simple. You just need to build a set of expanded states and show that it is a subset of itself together with the union of all these, because these we know they are dead already. And note that this is not a bounded conjunction or a bounded union disjunction, whichever way you see it. But for explicit sets, this actually works out if the explicit sets all are over the same variable and have the same variable order. So we can actually do this efficiently if these are all explicit sets. The other option we have, if we want to rather use BDDs for the expanded states, is that we, as I said, use this set SD. So we build one set that represents all dead ends as one explicit set. We also need to build the same set, but represented as a BDD. And we build a BDD representing all expanded states. And then this statement here just tells us, okay, this singular set representing all dead ends is a subset of the union of all dead ends. This is all in explicit, so we can use B2. Then we use B4 to kind of jump formalism from explicit to BDD. And then we can say that the set of expanded states as a BDD is a subset of itself, and the dead ends again represented as a BDD. So we can do this now because this is represented as BDD. And it's again a question, okay, do you prefer efficient generation or efficient verification? Again, the explicit sets might be more efficient generating the certificate, but the BDDs might be more efficient with verifying it. Okay, then let's get to the heuristics, interesting part. So how can we show, if a heuristic tells us the dead end, how can we show that this state is dead? Heuristics, and I will mention other heuristics afterwards, but only briefly. So if a delete relaxation heuristic tells us something is a dead end, that means some goal fact is unreachable, or some goal variable is relaxed unreachable. Now, if we consider all the variables that are relaxed unreachable from this set, so this is this from this state, this is this set R plus US, all the variables that we cannot reach from S in the relaxation, then we can build a formula that basically tells us none of these variables is true. And this formula represents the set of states where we can't, where none of the relaxed say, okay, if we are in any state, we cannot get to a state where one of them is true, else they wouldn't be relaxed unreachable. So basically we can say the progression of this set is the set itself. Furthermore, we know that there cannot be any goal state in this formula because this G that is relaxed unreachable is here in this formula. That is one of those V's. So the intersection of this set with the set of all goal states must be empty. And finally, state S must satisfy phi, simply because we're looking at variables that are relaxed unreachable from S. And if a relaxed unreachable variable from S is true in S, then we messed up something with relaxed reachability. So obviously it can't have any of these true. And we see again a trend that we've seen many times. We have this inductive set where we can't get out, and we can show this again with this rule progression goal that this set S phi is dead, and thus S must be dead as well. There is a comment from Malte, S phi I should say subset instead of equals. Yes, that's true. That's I was thinking equals makes more intuitive sense, but actually the statement equals is wrong, because it can be that certain states you don't reach from S1 within one step. Yes, so that's correct. Now talking about the representations, we see this is actually a very simple formula. This is just a conjunction of literals. We can literally choose any type of representation we want from the ones that we consider. A BDD is very simple. It's just a straight line, basically. It's a Horn formula because you have only unit clauses. It's also a dual Horn formula for that reason. It's a 2CNF formula, again, only unit clauses. And you can also represent it as an explicit set over the variables in this set here. So overall unreachable variables. Okay, this idea of unreachable variables can be extended to HM dead ends. So in HM, we don't have unreachable variables, but we have unreachable tuples. And actually, it turns out that if we build the same formula, just that we do here a disjunction over the variables in the tuples, this is exactly the same. It's an inductive set that contains no goal state and that contains state S. So this works actually exactly the same way. Now, if the representations were not that free anymore, we can still use Horn formulas because each clause contains only negated variables. We could also use 2CNF formulas if we have only the H2 heuristic. For H3, that obviously doesn't work because then we have size 3 here. And an important result is BDDs can no longer efficiently be used here in general. And that is a result that Stefan Edelkamp and I forgot the first name, Kissmann, showed in their paper here. By the way, all the papers that I reference, we have on the tutorial website, we have a bibliography slide, so there you can find all the information about these papers. The second HMax related thing I want to talk about is class learning state space search, which Marcel Steinmetz and Jörg Hoffmann introduced recently. This algorithm uses the HC heuristic, when it uses it basically to refine it to find dead ends better. So it's an iterative refinement of an HC heuristic. It's again the same concept. We can build the exact same type of formulas as with HM. And one nice thing about this algorithm is that usually it does as every heuristic search does. Once you have explored all the expanded states and everything else is just dead ends, it ends. But you can also continue letting it run until it can actually learn to detect the initial state as a dead end. And what that means is if you do that, you get actually a very compact certificate because it's just one of these formulas. Might be a bit bigger formula, but it's still better than having 10,000 dead ends. So this is a very compact certificate, and that can thus also be efficiently verified. But obviously we sacrifice planner runtime because the planner continues running even after it detected unsolvability already. And the last point I want to make about this algorithm is that you need to be very careful if you use additional sources of information. So one thing we did not know about in the beginning when we wrote certificates for this algorithm is that they use additional sources for mutexes, additional information. And we did not consider this information in our certificates. And obviously the certificates just told us, well, this is no proof of unsolvability. Something's wrong here. So always keep in mind what additional sources of information you might use. But it shows also that the verifier actually works as we want it to work. When we don't give the correct argument, then it will actually tell us. So that was also nice. As I promised before, I will also briefly touch on other heuristics, but this is very, very briefly. So one thing I can say is that all the lead relaxation heuristics are covered by this idea of the HMax dead end. So if you have the LM cut heuristic or landmarks that are based on the lead relaxation, they detect the exact same dead ends as HMax. So we can just use this formula for these types of dead ends. The other interesting heuristic is the merchant shrink heuristic, which also includes all PDB heuristics. And there we know that we can transform the merchant shrink representation to an ADD. And what we can do then is an ADD is basically a BDD, but instead of having true and false leaves, it just has numeric leaves. And it has basically for each heuristic value one leaf. And we are interested in the dead ends because actually the set of all dead ends in the merchant shrink abstraction is an inductive set. So what we can do is extract all these dead ends actually as a BDD. So we can, from an ADD, we can extract all states that lead to the same leaf into a BDD efficiently. This is, however, limited to linear merge strategies, because for nonlinear merge strategies, we cannot build this ADD efficiently. So there is that limitation. But PDB heuristics, for example, they are basically linear merge strategies, so they are covered by this approach. What is also noteworthy to see is we have here one set for all dead ends. As I said, we want to get all dead ends. This means we don't need to build for each dead end a separate proof, but we can just say, okay, all dead ends that we show to be dead with merchant shrink, we have this one set, we can just use that. This makes the certificate a lot more compact. And one last thing to mention is there is a small implementation detail in merchant shrink. Usually it merges unreachable and dead end states in the abstraction to the same abstract state. This is, however, bad for us because we count on the fact that this set is inductive. And if we mix the two different reasons for why these dead ends are not, or why these states are not interesting, then we don't get an inductive set anymore. It's neither inductive in the forward nor in the backward direction. So that is actually somewhat bad. And then our argument doesn't work. So what we need to do is actually disable that if we want to generate certificates. Okay, As the last example, I want to mention the H2 preprocessor that probably quite some planner developers know because it is used in quite a lot of planners. It was introduced by Vidal Alcazar and Alvaro Torralba, and it's a pre-processing step that simplifies the planning task. And how it does that is it incrementally performs H2 reachability analysis. So first in a forward direction, then in a backward direction, taking into account what we learned already, and then forward again, and so on and so forth. So I have here a small example. We have our planning task with the initial state, a set of goal states, and the first H2 reachability analysis detects certain tuples or certain pairs of facts that it knows we can't reach from the initial state. So this is our first dead set here. And then the backwards iteration will basically see, okay, assuming I am in the goal state, but only in the goal states that don't violate what I know to be dead already, what can I now backwards reach? And it will basically tell you, okay, these states I can actually not reach backwards. Maybe I could reach them if I would go over this already before red area here, but if I am not allowed to go here, then I cannot reach this. So this is an iterative refinement procedure that at some point reaches a fixed point. Now, how does a high-level certificate for this look like? For this, I need some terminology. I call DI the set of literal pairs that are shown to be dead before or in iteration I. And what I mean with shown to be dead is we know that any state that satisfies these two literals at the same time, any state that does that will be dead. And then I define a set SI, which is basically all states that exactly don't satisfy these literals at the same time. So all the still alive states, so to speak. Now, if we start with iteration 1, we define D0 as the empty set because we don't have anything shown dead yet. This has a nice side effect that we can already state that the negation of S1, so all states that violate these, it's not mutexes, it's dead pairs we call them, all states that violate that, no states can violate an empty set of dead pairs. So the negation of that is actually the empty set because S0 is still all states. So we, for our argument, we're actually going to show each iteration that this the negation of this new set is dead. And we can assume for each iteration that the set Si-1 is dead already. So that we always can assume as given. And how can we now argue that the negation of Si is dead? In a forward iteration, we know that the initial state is still in Si because that we can reach, that cannot contain any dead pairs. It did not before, and because we start from I, we cannot suddenly exclude it. Then we know the progression is either of Si, is either in Si, or it goes to a state that was before already violating one of those dead pairs. So it goes to Si unified with the negation of Si-1. It's basically this here. It cannot happen that it goes to this place here that's not in Si anymore, but that was in Si-1. And from that, we can actually conclude directly with rule PI, progression initial state, that the negation of Si must be dead. So all this part here that is not part of Si is dead. The arguments for a backwards iteration is somewhat similar, but we need a bit more steps. So again, we can assume that Si-1, the negation of that is dead. What we can observe is all states that are now after this iteration, all goal states that are now dead must have been dead before. It's the same argument as with the initial state. We can't suddenly detect new goal states as dead in a backwards iteration because that's where we start with. So from that, we know because this set is dead, we know that this expression here must be dead. Furthermore, we can say the regression of Si leads only to Si or to the negation of Su. So this is basically, again, we cannot have a step that leads from Si to this I-1 here, which is not in SI anymore. And from this, we can apply a rule called regression goal, which is, again, it's one of those similar rules that I didn't really go into detail, but this directly shows us already that the negation of SI must be dead. And it intuitively also makes sense because it might be that we can somehow reach one of the states here backwards, but we would need to go over SI-1 negated, and that we know already to be dead. So it doesn't make sense to look at any state in here. Again, some remarks about this. First of all, how can we represent the state? It's very similar to H2 again. So we have all these dead pairs, and we just say not P or not Q if the two literals are P and Q. And this formula can be represented by 2 CNF. Important to notice here, horn is not suitable anymore, because it could be that P and Q are negated literals. So the negation of it is actually a positive literal, and then we don't have a horn formula anymore. The second thing to note is the H2 preprocessor can actually detect the task unsolvable already. If that's the case, we can easily extract the full proof. So if it would detect the task unsolvable during a forward iteration, what happens is actually it will see, hey, I can't reach any goal states anymore. So that means the set of all goal states is a subset of the negation of set Sn. And set Sn has been shown to be dead, so all goal states are dead. And it's the same argument in a backward iteration, just that it will tell us I can't reach the initial state anymore, so thus the initial state must be dead. But even if the preprocessor cannot detect the task unsolvable, we can still use this knowledge that the negation of Sn is dead to explain why we're never actually considering certain states. As I said before, what this preprocessor does is it simplifies the planning task by simply ignoring certain facts or actions, because we know this could only be applied in a situation or would lead to a situation where we would violate these dead pairs. So we can use this to explain why we never look at that. And what we could also do is we could extract some more fine-grained statements, such as if we just take one dead pair and we take the P and Q as a formula, we know all states that satisfy this formula, so S, P, and Q is dead. And we can actually extract statements like this within the proof system. So that's also very nice to maybe make the certificate a bit more fine-grained when we just are interested in that this particular pair is dead. Okay, then that reaches the end of our tutorial. So to recap, I have here a couple of take-home messages. The first one is that you hopefully learned how we can verify algorithms on different levels of trust, with unit tests, with certifying algorithms, and with theorem provers. Next, we have shown that we have this unsolvability proof system that incrementally deduces knowledge about dead states. So that's what we're mostly interested in. The modularity of these proof systems enables us to combine different sources of information, so we can take different heuristics, we can add pre-processing, and so on. Whether or not such a certificate can actually be verified efficiently depends very much on the representation of state sets, or in an abstract sense, which operations these representations efficiently support. Different representations can offer different trade-offs between efficient generation and verification. And usually, as you've probably noticed, this theme of reachability argument of inductive set, usually generating certificates involves this kind of argument. And I just want to give a little bit of a quick outlook what more we can do with this. So of course, one thing we're always interested is that we want to cover more planning techniques. Things we're currently interested in is dead-end potentials. So there are potential functions that basically they give a numeric value to states, and they can guarantee that each successor has a higher value than its predecessor, but the initial, and you so you start here, you can only go up, but you somehow need to go down to reach the goal. And that is an unsolvability argument that we would very much like to translate into a certificate. It is actually, from a conceptual idea, it's very easy to explain this. These states that have a certain heuristic value or higher, these sets are actually inductive. The big problem is, however, we didn't quite figure out yet how we can efficiently represent such a state set, because the potential heuristic is based on numerical values and not on logical formulas. So that is one open question that we're currently investigating. Another thing that we did not really look into yet that would be very interesting is things like partial order reduction, symmetries, and so on, because they also they ignore parts of states that would be reachable, but we need to somehow argue why we don't need to care about them. And other form of task transformations would also be interesting. Now, it can be that if we cover more and more planning techniques, at some point we notice, okay, this proof system lacks something to efficiently express what we want to express. Like, for example, with the dead-end potentials, maybe we just need a different formalism. So that is one thing that we can extend to verifier with. So we could look at more representations. And I think Malte mentioned it in the break or in the chat already. We have actually a talk in ICAPS this year where we do exactly that for CNF formulas. I mentioned before, CNF is kind of tricky because it's an NP-complete problem set. So verifying sentential entailment on CNF formulas is not that trivial. But the trick is basically that we can use certificates from SAT solvers. So this modularity that we use different certificates within the proof system. And it can, of course, also be that we simply need some more inference rules. There's always a bit the question, do we want to add more and more, or do we want to keep it as compact as possible? So like with conclusion initial and conclusion goal, do we really need the two? Ideally, we don't want to just add them just for having them added. We want to have a reason, but we're also not saying it needs to be as minimal as possible. And lastly, of course, what we would also like to do is verify the verifier. Thank you very much for your attention.